So as I said on Wednesday, my goal is to try and figure out how to do this without just plugging and chugging all 230 options. So I start to think about what we did in the real case over here. I simply divided by 3, multiplied by a third, right? And I did that because 1/3 and 3 are multiplicative inverses. Let's extend that to this idea. In Zm, that means the integers mod m, the numbers from 0 to m minus 1, simply treated as remainders. I'm going to call the multiplicative inverse of a another integer. I'll call it a with a bar on it. If a times a bar is equal to 1 mod m. Well, I should use congruent here. So let's think about some small examples. Let's think about mod 9. Well, 2 times 5 is 10. That's congruent to 1 mod 9. So if I had an equation that was 5x congruent to 3 mod 9, instead of, quote, dividing by 5, I could multiply by the inverse. I could multiply by 2. If I multiply both sides by 2, what happens on the left? Except I'm working mod 9, right? And in mod 9, 10 is 1. So over here, I just get x. What do I get over here? I get 6. Hey, wait a minute. Go back to the original equation. 5 times 6 is... What's the remainder when you divide 30 by 9? Isn't that what I wanted? I solved the equation. Because I knew there was an inverse. As a matter of fact, if I'd had a 2 here, I could have multiplied by 5, right? If I had an equation 4 times 7, 4 times 7 is 28, that's also congruent to 1 mod 9. So I had an equation like 7x equals something or 4x equals something. I could multiply by the other one and I would solve the equation. 8 times 8 is, and when I mod that by 9, I get 1. So I have an equation that says 8x equals, I multiply by the inverse of 8, which is 8. So if I know the multiplicative inverse, I can play this game and multiply by the inverse. However, if I am working in the universe mod 9, The only numbers I'm allowed to use are the numbers from 0 to 8, right? 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. So the remainders, mod 9, are 0, 3, and 6, right? Keep going. 3 times 3, the remainder is 0. 3 times 4, the remainder is 3. 3 times 5, the remainder is 6. Because I'm dividing by 9. 3 times 6, 18, the remainder is 0. 3 times 7, 21, the remainder is 3. 3 times 8, 24, the remainder is 6. Three does not have a multiplicative inverse, mod 9. Neither does 6. Neither does 0. But that makes sense. You shouldn't be able to divide by 0 anyway. Why? What's different about that number than 2, 5, 4, 7, and 8? Okay, every single multiple of 9 is also a multiple of 3. I can't ever end up with something that's 1. What's another way I can phrase that in terms of the stuff we talked about Wednesday or last Friday about primes? The greatest common divisor of 2, 5, 4, 7, and 8 with 9 is 1. Greatest common divisor of 3 and 9 is not 1. 3. Numbers have multiplicative inverses when they are relatively prime. I am going to prove this theorem. And the proof comes from Bézou's coefficients. The whole reason for me to do that S and T garbage from Wednesday is to do this. Bézou's theorem said, whatever our greatest common divisor is, means we can write that as S times the first number plus T times the second number for some S and T. Wait a second. That means that S times A is 1 minus Tm. Which means SA is 1 bigger than a multiple of M. SA is congruent to 1 mod M. Check. There you go. The number I need to be the multiplicative inverse is the number S I get from Bézou's coefficients. So that means if I want to solve this, what do I need to do? I need to do the Euclidean algorithm, find out if the greatest common divisor is 1. If it is, find S. I prepped this after last class, which is why it's in a different color. Here we go. I need the greatest common divisor of 232 and 89. Time to start dividing. Get out your calculators. Let's rock and roll. $90, $182. So it's going to be 289s with something left over. Now step these numbers over. 89 goes here. 54 goes here. Well, 89 is 154 with something left over. 54 is something 35 with something left over. $35 is some number of 19s with something left over. I'm sorry? 1 and 16. 19 is 116 with 3 left over. 16 is 5 times 3 with 1 left over. And 3 is 3 ones with nothing left over. There's my greatest common divisor, and it's 1. Yay! Now for the crappy part. This wasn't the crappy part. No, this was the easy part. Now I have to do what we were doing last time and work this crap backwards. I need you to write 1 as some number of 232s plus some number of 89s. And that requires me to rewrite each of these and use them and regroup. So here, 1 is 16 minus 5 threes. Now use the line above that. 3 is 19 minus 16. That is 6 16s minus 5 19s. Because I got 5 16s here and another one in front, right? Now we use the one that's got a remainder of 16. 16 is 35 minus 19. So I replace this. How many 19s do I have now? And 6 35s. Well, now I go up to the one where the remainder is 19. The remainder is 19. 19 is 54 minus 35. Regroup. I have 11 35s here, and I have 6 more in front, so that's 17 35s minus 11 54s. 35 is the remainder up here. Replace 35 by 89 minus 54. So I'm going to have 17 89s. And how many 54s? Negative 28 54s. 54 is the remainder in the very first division we did. Replace 54 by 232 minus 2 89s. Got to keep the 2 with it. If you want, you could even put another set of parentheses there rather than just a dot. So you remember that there's that 2 is there. Now regroup. How many 89s do I have? I got to multiply that in, don't I? 2 times 28 is 56. 56 and 17 is, you all have calculators in front of you. You do not have to stare at me like I'm speaking Farsi. 73. And then here I have 28 232s. The other side of this equation is a 1, right? 1 equals number times 89 minus number times 232. That number, that's my multiplicative inverse. 73 is the multiplicative inverse of 89. Mod 232. So only when I am working in the 232 universe does that hold true. By the way, if the number was negative, like let's say the negative number ended up here and the positive number ended up here, then I could just add 232 and get the thing it was equivalent to in the positive sense, right? I could just go one more loop around 232s. Okay, so what? How does this help me? Remember, my goal is to solve that equation. How do I solve that now? I need to divide by 89. But I don't know how to divide in mod 232s. So instead of dividing, what do I do?
You multiply by 73.
I multiply by the inverse. Since I am working mod 232, the left side becomes 1. Because it's negative 28 232s with 1 left over. What's 73 times 5? Mod 232? I found my answer. Now I want you to imagine doing this. Only instead of the number I'm using, 232, the number I'm using is 45 digits long. And the number over here on this side is something around 20 digits. Why 20 digits? Because that's roughly 64 bits long. This is an encryption. I take the message you want to send, multiply it by some long number, and do mod some other big number. And instead of sending the unencoded message, I send the encoded message. How do you decode it? You multiply by the inverse of my encoding. This is the way RSA encryption works. It's just that the numbers are fucking huge. Every time you see that little lock on a website doing SSL security, they're doing this, only the numbers are even bigger. Modern SSL uses 256-bit numbers. That's 80 digits long. It's a hell of a key, isn't it? How else are you keeping your credit card information safe? This is not short. This took a half an hour. This is absolutely trivial to code. The entire process of the extended Euclidean algorithm, which means do the greatest common divisor and then do the Bézier coefficients, is big O of log n. It is a very fast algorithm. Questions? If you are interested in more details on the way in which this sort of encryption algorithm works, you should look at chapter 4, section 6 of this text. It will go through all the way through RSA encryption and its relation to this behavior. There's an exponential in there somewhere as well, just to make the encryption even more complicated. Solving a congruence is like solving a linear equation. And I learned how to solve linear equations back in algebra class. And immediately after I learned how to solve linear equations, down the line I said, well, what if I have two lines? They might cross, they might not, they might be the same line. Remember that garbage? What if I have simultaneous congruence equations? The following riddle is 2,000 years old at least. A farmer taking their eggs to market drops the basket. None of the eggs break. When they pick them up three at a time, there are two left over. When they pick them up 5 at a time, there are 3 left over. When they pick them up 7 at a time, there are 2 left over. How many eggs are there? The first written version of this puzzle is in Chinese. And I believe it dates to the 100s-ish. I want to find a number, the number of eggs, so that the remainder is 2 when I divide by 3, and the remainder is 3 when I divide by 5, and the remainder is 2 when I divide by 7. How do I find this number? Well, this has to be a reasonable number of eggs because the single person was carrying it, right? Nah, maybe this basket was carved. 7,800 eggs. I don't know. Because this puzzle was first written in Chinese, the theorem that solves it is known as the Chinese remainder theorem. And when the numbers that are the moduli are small and pairwise relatively prime, there's actually a constructive method to find this solution. These are the moduli, M1 through Mn. In our case, we only have 1, 2, and 3, but I could have as many as I want. And A1, A2 up to AN integers, where X is congruent to A1 mod M1, X is congruent to A2 mod M2, and so on. X is congruent to AN mod MN. Then this system has a unique solution modulo capital M. M is the product, I equals 1 to N of little m. It turns out that the proof of this theorem is actually constructive. It tells me how to solve it. If I let this m be the product of all of the little m's, I equals 1 to however many there are, I'm going to create a new value, capital M K. And that's going to be m divided by little mk. Remember that the little m's are pairwise relatively prime, yes? That's what it said up here, pairwise relatively prime integers. that means that the greatest common divisor of little mk and big mk must be 1. Hey, wait a minute. The theorem I just proved about inverses required the greatest common divisor to be 1, right? That means there's an inverse for little mk in the universe of capital MK. Wait, reverse those. Capital M here, little m here. Why? Because the little m's are the modulos. Sorry. Remember, the little m's up here are the modulos. So yk times capital MK is equal to 1 mod little mk. Congruent. So what do I do? Well, my goal is not to get 1, it's to get A. That's what these equations say. I want A, right? So what I do is I take the sum of AK times YK times MK, K equals 1 to N, and that's our X. At this point, my answer is you got to be kidding me. Our example was this, right? This was my Chinese puzzle, my eggs. So this is A1, this is A2, this is A3, this is little m1, this is little m2, this is little m3. What is capital M? Scroll back up here. Capital M is the product of all the little m's. That's 3 times 5 times 7. Equals? Yes, calculators again, it's a good thing. 105. Now, M1, capital M1 is 105 divided by 3. Capital M2 is 105 divided by 5. And capital M3 is 105 divided by 7. I divide by each of these m's. But notice that means I'm taking one of these 3 numbers away, so I just multiply the other 2. So 105 divided by 3 is 5 times 7. 105 divided by 5 is 3 times 7. 105 divided by 7 is 3 times 5. With me so far? This is gross. Here's the deal. I need the multiplicative inverse of this number mod this number. So 1, I need the multiplicative inverse of 35 mod 3. Hey, wait a minute, 35 is bigger than 3. What's 35 mod 3? 33 with 2 left over, right? This equation just became 2y1 congruent to 1 mod 3. There are only 3 numbers to try, 0, 1, and 2. Because I'm in the universe mod 3. It's definitely not 0, because 2 times 0 is 0. It's definitely not 1, because 2 times 1 is 2. What's 2 times 2? But I'm in the mod 3 universe, and that's 1. Now let's do the second one. The second one, 21y2 congruent to 1 mod 5. But I'm working in the mod 5 universe. 21 is too big. What's 21 mod 5? That's nice and easy. 1y2 is equal to 1 mod 5. I'm done. y2 is equal to 1. Do the third one. 15 y3 congruent to 1 mod 7. 15 is too big. What's 15 mod 7? 14 with 1 left over, right? That means that 1y3 is equal to 1 mod 7. I know what y1 is, I know what y2 is, I know what y3 is. I found all 3 of my inverses. The numbers were nice and small, so finding the inverses was actually pretty easy. If the numbers were a lot bigger, I might have to do that Bézier crap. Ugh, I can do it, it just sucks. But now I know my value of x. X is a1 times y1 times m1. a1 is 2, y1 is 2, m1 is 3, plus a2 times m2 times y2. Oh, wait a second, wrong m. 35. Capital M, not little m. So here it's 21. These numbers. And then it'll be 2 times 1 times 15. Give me that number. Okay, hang on a second. There was one more m value. The capital M I started the whole thing with, right? What is this number? Capital M. What was the number we came up with for capital M? 3 times 5 times 7. What is 233 mod 105? 23. If you have 23 eggs and you pick them up 3 at a time, you pick up 21 of them, there are 2 left over. If you pick them up 5 at a time, you pick up 20, there are 3 left over. If you pick them up 7 at a time, you pick up 21, and there are 2 left over. Those are the equations I wanted to solve, weren't they? Son of a Okay. I like this theorem. I like it because it is a constructive theorem. If I can remember what to do at every step, I have an algorithm for this. This is solvable directly. But I don't think this is a particularly straightforward algorithm to remember. That's why I have it written down in front of me, people. I don't have this thing memorized. Trying to memorize this is like trying to, oh no, forget it. I'm not even going to go there. No, I don't want to memorize this. When I have pairwise relatively prime moduli, there is another method that works just as well. The alternate method is called back substitution. Let's start with one of the equations. Actually, I'll start with the smallest one. X is congruent to 2 mod 3. The definition of being congruent to 2 mod 3 means that X can be written as 3 something with 2 left over, right? But I also know that I want X to be congruent to 3 mod 5, yes? But this is X. So 3k plus 2 should be congruent to 3 mod 5. Right? But wait a second. Subtract 2. 3k congruent to 1 mod 5. Oh, this is finding an inverse, isn't it? What's the inverse of 3 mod 5? I don't even need to go there. K must be 2. 3 times 2 is 6. 6 mod 5 is 1. That worked. So K is 5 something else with 2 left over. Because there's a mod 5 here. Back sub. Put this back in here. And that means that X is 3 times 5t plus 2 plus another 2. That's 15t plus 6 plus 2 plus 8. Yes? Go to the third equation. What's the third equation about X? X is congruent to 2 mod 7 means that 15t plus 8 must be congruent to 2 mod 7. But I'm working mod 7. 15 is too big. 8 is too big. What's 15 mod 7? $14 with 1 left over. What's 8 mod 7? What's the value of t? Subtract 1. Now back substitute. What's X? 15 times 1 plus 8. 23, son of a bitch. By the way, we were working mod 3, then we were working mod 5, then we were working mod 7. So this result is mod 3 times 5 times 7, 105. Bing! This, I think, is more intuitive because I don't have to remember the construction of I need Y, I need capital M, I need little m. I think this is easier. But requires you to go through them in order and keep track of all the mods separately. We did our modular exponentiation as well, right? We raised numbers to big powers and we did the mod whatever. I think the number we did the example in the textbook is mod 645 or something like that. Ew. I'm making this one a little easier. I've decided to do this problem mod 13, and 13 is prime. Pierre Fermat, Fermat's last theorem, same Fermat. Fermat said, you know, when you're using a prime and you do a number to a power, the result, if your power is p minus 1, is always 1. Or a to the p is congruent to a if you add one more multiple on each side. Now, why does this help me? What possible benefit could I get out of this? I want to do 7 to the 121st power. I don't want to think about what my calculator is going to show me. But I do know that I'm going to do it mod 13. So if I did 7 to the 12th, what would I get? Mod 13. By this Fermat's theorem, I get 1, right? By the way, this result is called Fermat's little theorem. So how do I do 7 to the 121st? Answer, I write 121 as something times 12 with something left over. Quotient remainder again. What's my quotient? What's my remainder? So I can think of 7 raised to the 121st power as 7 to the 12 times 10 plus 1. When you are adding powers, that's the same as multiplying the bases, isn't it? And when you are multiplying powers, you can think of that as power of a power, yes? Notice those are all equal signs. I'm going to throw in a mod 13. 7 to the 12 to the 10 times 7 to the 1 mod 13 means I do this mod 13. What's 7 to the 12th mod 13? I'm done. 1 raised to any power is just 1. And 7 to the first is just 7. I have no idea what 7 to the 121st power is. But I know if you divide by 13, the remainder is 7. Writing a number in terms of its remainders can actually save space when you are dealing with very large numbers as terms of computer storage for passwords. This is why you can use fewer and fewer digits to encode larger and larger messages. You don't actually have to store the message, you can store the remainders. Again, there's a lot of neat pieces of encryption that come out of this. The rest of chapter 4 is devoted to that. So all of you cybersecurity people should read those carefully. I will see you on Monday. Have a wonderful weekend. 4.3 is due then.